Hello, hello. It is time for lecture 22, 22, 22, 22. Yeah, ha, 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 lecture 22. Holy moly. Building upon lecture 21, but really cycling back to sort of the beginning of the semester, the push toward our whole understanding of contemporary theories of the universe, right? What was the deal? What was so important? What was the thing that we were first able to use to figure out how big the universe was, what the universe was doing, and how the universe has aged? Galaxies. That's right. We were trying to figure out how those galaxies represented the universe, right? And so, in so many ways, this is an example of how science works. When we're trying to understand the contemporary theories of anything, we usually look at observations, right? We start again with facts. This is our handy dandy outline of the scientific theory creating process, right? A version of what people call the scientific method. We have these facts. We know about spiral nebulae. They sort of exist, right? But what are they exactly? Then you try to gather data about them and figure out what they are, right? And when you gather those data, you see certain laws and you see certain things happening. You realize, these objects are moving away from us. And the further away they are, the faster they're moving, right? That was the data, the information that led to the Hubble law, which was the expansion of the universe, right? And the whole concept of the Big Bang and the way that we learn about things came originally from trying to study these spiral nebulae, which we then realized were galaxies, just like our Milky Way. And then when we brought the theory forward from the Big Bang to our present day, let me see if I can find, yeah, here we go. Right? We started out from all the stuff at the beginning, right? Big Bang to the Planck time, inflation, symmetry breaking, energy, quark gluon soup. Particles start to appear, those standard model particles we know so well, the quarks and the leptons and the bosons. And then we have nucleosynthesis, right? Which leaves us with hydrogen and helium. And then further on, right, that matter decouples from the energy. They recombine, the atoms do, the atomic nuclei with the electrons to form neutral atoms. The cosmic background radiation released, large scale structure starts to form as the galaxies start to fill in, right? They start being made. At this point, it takes hundreds of millions of years, but those things are assembling slowly but surely. Meanwhile, because of hierarchical structure formation, little things are still happening. Things are pulling together, right? You have 300 million years after the Big Bang, the first stars are evolving. And as they are born and then they live and then they evolve and they explode as supernovae, you're creating new elements through stellar nucleosynthesis. Remember all that good stuff? I mean, and then we have black holes too. They are being created as the result, as the byproduct of all that collapse, right? Stuff isn't blown away. A supernova ejecta, right, turns out into these kernels of matter that are so concentrated that we can't see beyond a certain Schwarzschild radius. Inside them is completely unknown. Right, we think there's an event horizon on the outside and a singularity on the inside, but who knows? There could be pink elephants dancing in there, and we have no idea. That's the beauty and also the mystery of black holes. And all of that is leading up to the point, right, where the universe is being reionized. These bright stars, these black holes that are created as gravitational engines producing QSOs, quasi-stellar objects, or quasars, right? They are creating an environment where finally all of that fog, all that neutral atomic material is being ionized and blown away in a way that you can shine light through it, just as what we see today out in the universe. It is amazing. It is awesome. It is beautiful. And now, a full billion years after the Big Bang, things that we recognize as galaxies are appearing again. Those galaxies that Edwin Hubble and others, Harlow Shapley, Heber Curtis, all those great names from early in the semester, right? Hope you haven't forgotten them. You can go back there and take a look too if you want, trying to figure out, are these things inside our own Milky Way or outside our own Milky Way, right? And there we have it. Today we know they're outside the Milky Way. What is their structure? What is their connection? At the end of the last lecture, remember I told you that galaxies are to the universe as cells are to the human body. When we study them, we understand better what the universe is all about, right? We have trillions of cells in our human body. We don't really understand every single one of them well, but we understand categories. We understand groups of them. We understand where they might be, how they congregated, or if they're distributed, what function do they serve? What indications do they give when we see them in this part of the body or that part of the system, that sort of thing, right? And so the careful study over the decades of galaxies and so forth is really leading us to understand that aspect. So there's a lot of information about galaxies, which I'm happy to share with you. It's in the textbook. And so a lot of this section, this lecture, this study guide, hope you're filling out your study guide already, right? A lot of it has to do with materials and information that is available in the textbook and is described very, very effectively. And so I'm going to point you to them. I'm not going to overly redundanty, whatever, talk about them in this lecture, but the lecture, I'm distilling the theories, the contemporary ideas that matter. And so we're going to go to the textbook, we're going to go through it. I'm not going to read it all, but I'm going to show you what you need to read and understand later about galaxies. And from there, understand, that's how they fit within our universe. Okay. Now, our galaxy is not one of the very first galaxies that formed around redshift 7. A little bit later in this lecture, I'm going to explain or describe, based on our evidence, what we've seen in our own Milky Way about what redshift, or about how many billions of years after the Big Bang, or how many billions of years ago, our own Milky Way was formed. And then from that, we can get a sense of when our solar system, our sun, all that was formed, right? I'll give you all that information. And if you've taken other astronomy classes, you may already know this, but that's okay. We are going to go through this in the context of contemporary theories of the universe. It'll be beautiful. Okay, here we go. The lecture material that I want to share with you on the astronomy OpenStax textbook, 2nd edition, right, is right here, chapter 26. This is the first part of chapter 26. Our Milky Way galaxy looks kind of like this, okay? And notice that depending on whether you're looking at it through a camera that takes pictures that our eyes see, or if you're looking at a camera that sees X-ray emissions, all right, this is the description here, you see different things going on. And indeed, that is because what we see, remember the electromagnetic spectrum earlier on in the semester, right? When you understand how the electromagnetic spectrum works, you realize that each thing has a different result coming out. This optical picture over here, the red indicates gas that's glowing because stars are bathing them with radiation. These dark streaks represent dust that's streaking around, and notice that they're in these spiral patterns, right? And then the bright blue things here indicate regions where there are stars that are brightly shining and causing their blue light to reflect off of a material that's coming to our eyes and so forth. So blue stars, and then it's just a beautiful combination of material, right? And then the center here, these yellowish stars, they indicate that they're older, billions of years old. These may be only millions or even less. Recently formed stars, thousands of years old, perhaps, who knows? But there's a lot of them, that's for sure. Now, over here, again, if you look at the X-ray light that's coming from these things, right? It's a whole different ball game. You can see still some of the bright things, but notice the center is super bright, right? The center here is like dark, but the X-rays, they can blast through all the old star stuff. And what you're seeing is a supermassive black hole in the middle, bright young stars in the middle. And then that supermassive black hole is doing stuff, right? Through that gravitational engine thing. This is not exactly a quasar, but it's so bright. It's generating lots and lots of light coming through. And look at all these colors, right? And they're shown in purple. added to all the other colors, which are superimposed on top of this, right? And so you see that the contrast is different. So you can see where the X-rays are coming from as opposed to where the visible light is coming from. It is all really neat. And all of this material comes together to give us an understanding of what all these different things go. Okay, so chapter 26 intro as a start, and we're going to look at 26.1. This you already kind of know, right? We talked about this a little bit, so this is kind of a refresher. But remember how there was that Edwin Hubble guy and figure out stars in the great spiral galaxy, a great spiral nebula back then in Andromeda, right? And so it was 100 years ago that people, with the help of Edwin Hubble being the first one, kind of figured out what was close by and what was far away. And I remember mentioning Immanuel Kant as well. Remember in the 1700s, suggesting that based on what he saw, right, the rules or the data from the stars, he had hypothesized that the Milky Way galaxy was not the only one, and those other objects could be galaxies as well, right? So remember, all of these things came together with Edwin Hubble figuring out that this beautiful galaxy, right, which was then called the Great Nebula in Andromeda, turned out to be a spiral galaxy just like the Milky Way. Now, we don't see spirals, it just kind of looks like a flat frisbee, but realize that we're looking at it edge on, right? Remember, this is as flat as pancake, actually flatter than a pancake. Its flatness, its thickness is only 1% that of its width, right? Typical pancakes are not nearly that thin, but this is really, really broad and wide, and there's all this glow around the outside. So we're looking at it just a very light angle. That's another smaller galaxy nearby it. That's another smaller galaxy nearby it. So each of these are galaxies too. They might be a little bit smaller, but they're significant objects. They contain millions, maybe billions of stars, right? And this galaxy, the Andromeda galaxy, contains hundreds of billions of stars. Pretty amazing, right? And then remember, here's that Edwin Hubble guy. And so read this if you feel like it and understand what the description and the explanation was. Very quick read, but a good review of the stuff that we went into in quite a bit of detail at the beginning of the semester, right? When we were first trying to understand the most important contemporary theory of the universe. So after those galaxies were discovered, right? The first galaxies were actually discovered quite a long time ago. William Herschel and his sister, Caroline Herschel, they were German-born scientists and musicians, if you can believe it. They are actually originally like court musicians in King George II, I think is his court. And anyway, King George III helped them become real astronomers. Like they helped them build a big observatory in Europe, in Britain, and they took a lot of really neat observations with big telescopes on the biggest, I think the biggest telescope in the world at the time. So Caroline and William were sitting there and like making maps of the sky and saw a whole bunch of these spiral nebulae and blobs that clearly weren't individual stars, but like conglomerations or collections of stars. Okay, and so those were put in a catalog, which eventually became known as the General Catalog. And then as it got updated, became the New General Catalog, or the NGC, the New General Catalog of Galaxies, which is really, really cool. And so these galaxies, there were thousands of them. All right, 7,008 or 7,900 of them, to be more exact. And then later on, I believe it was William, did I say John? I meant William Herschel and Caroline Herschel, right? Sister, brother, pair. I don't know if I said that. I had to go back and take a look at the video. Anyway, it's William Herschel and sister Caroline Herschel. They were the Herschel sibs, and they really created the New General Catalog. And then later on, John Herschel, whom I believe is William's son, wound up doing even more stuff in areas in the southern hemisphere, looking up parts of the sky that were not visible from England. And they created this wonderful catalog of thousands and thousands of these things, which turned out to be galaxies, right? Like our Milky Way and unlike our Milky Way, but all of them far away, as it turns out, thanks to Edwin Hubble's discovery. So if you come across these people's name, don't be shocked. William and Caroline Herschel, and then the next generation, John Herschel. Okay, all right. So moving on, let's go back again to the screen. The types of galaxies that people found, right? You want to describe the properties and features of spiral, elliptical, and irregular galaxies and explain what might cause them to change in appearance over time. So that's the learning objectives of this particular chapter. So make sure that you learn those, okay? And so here's a spiral galaxy. Now, modern day spiral galaxies, some spirals, because spirals turn out they're like the patterns in the swirling dust and gas and stars that are swirling around in this huge galaxy. So these spiral arms are not permanent features of the galaxy, right? This is something that took a long time to figure out too. It's also part of the theory of galaxies, scientific understanding of how galaxies do their thing. And then you have on the edge, if you look, what you really see is this is like an edge on, it's a disc, right? It's like a frisbee or it's like a pie plate or something like that, right along the edge and looking right down the edge. We can't see any individual galaxy going all around it because they're so far away, right? We just can't get the perspective. But we can put lots of different pictures of different galaxies together with similar characteristics and deduce what a three-dimensional shape might look like. But these are nice views, right? Here's a really, really sharp view of a galaxy that's straight edge on, almost exactly. And you can see that sort of brownish, blackish dust in the middle and the brightish glow from the stars. Meanwhile, this face-on galaxy, right, Messier 100, another person, Charles Messier, M, right, is named after him. He put together a catalog of about 100 objects, which are a little bit different from the Herschel's catalog of thousands of objects, but still very important and valuable and cool pictures and cool objects to look at. So here are these spiral arms here and here that you can see on the face-on spiral galaxy. And then here, look, some of these galaxies, they have these bars. Look, the spiral arms don't start in the middle. They go straight out along this ellipsoidal rugby ball shaped bar thing, and then they start at the ends of the bar. Right, this is NGC 1300, new general catalog from the Herschel dudes, right? And you can see that this is a barred spiral galaxy, B-A-R-R-E-D, barred spiral, okay? And these are also disk galaxies, but they have these little box, peanut, rugby ball shaped things there. Turns out our Milky Way galaxy has a bar in the middle. That's right. Its bar is maybe comparatively, like if you look at this galaxy, this Milky Way bar is only maybe a third the length, maybe even a quarter the length of this very, very impressive bar here. So it's kind of a shortish bar, but it's got big spiral arms that come off this bar. So it's really, really neat. And this was only really confirmed maybe 20 years ago. Right, we've known about our Milky Way for a really, really long time, but it was well within our lifetimes that we didn't figure out until recently that the Milky Way actually had a bar in it. So it's just kind of cool, right? This is all still living science. We're still learning lots of new things. Anyway, Edwin Hubble basically showed that if you could try to categorize galaxies, right, there were elliptical galaxies, things that looked almost perfectly round, and there seemed to be no disk at all, right? And then they become increasingly flatter and flatter. So you can find these sort of ellipsoidal galaxies. And the larger the number between E0 and E7, the flatter the thing looks, right? Basically, the ratio, right? If you compare this length and that length, right? This length and that length. So the larger the number, the longer that major axis is compared to the minor axis of this elliptical galaxy, until you get a thing that kind of looks like a lens. They call that an S0 galaxy or a lenticular galaxy, something that's just sort of starting to look like a spiral, kind of the transition point between an elliptical galaxy and a spiral galaxy. And then you get these S0s, SAs, SB, SC. Notice how they are much more sparse, right? The galaxy is much broader. By the way, this is not a really good picture of a spiral galaxy. I just want to tell you, spiral galaxies don't look like, sea anemones or spiders and stuff. Galaxies usually only have at most 4 arms. They usually have 2 arms. Sometimes they have 4 arms. Notice that the arms just happen to be thinner and more spread. So it gives the illusion of having numerous spokes coming out of a wheel. In fact, it's just 2 arms or maybe 4 arms, and they just happen to be more spread out as opposed to having a larger blob, right? So the lowercase letter A, B, and C show you how far spread apart and how, say, sparse in between the spiral arms are. Whereas the capital B there means that there's a bar in the middle. And then similarly, the spiral arms are still use the lowercase letter to sort of show how that goes. So that's a description. Here's your elliptical galaxy here, right? This is a big elliptical galaxy. Notice how it's kind of a blob, right? You don't see any spiral arms in there. There's other little galaxies in the vicinity, which is worth talking about. But notice how they have different shapes, right? And some of them are most of them are farther away. That's why they look so small, not that because they're tiny compared to this, although there are tiny galaxies compared to this one. This is a really big elliptical galaxy, right? Now, this thing here is an interesting object. Notice it kind of looks like a spiral, but look like it's got streaks and it's got this little loop over here, right? So this is an unusually shaped elliptical galaxy. We might call that a peculiar galaxy. How do you create this kind of thing? As the caption suggests, you got to smash other galaxies together, okay? So here's a dwarf elliptical galaxy, a little tiny one. This is a black and white picture, Messier 31. Remember that little blob that was just right near Messier 31 or the Andromeda galaxy further up? Let's just slide back up there. Sorry if your eyes are kind of a little bit zipping around for the moment, but if you go, well, let's not. If you go back to the previous page and see the spiral galaxy in Andromeda, there's a little football-shaped thing in there, and that's Messier 32, M32. And then see these irregular galaxies like that? If you can believe that, this is the Milky Way galaxy viewed from the Earth, right? This is the disk of the Milky Way. Remember, we live in the city of dreams. Oh, wait, if you know that song, send me an email. You get a point. Remember, 1,000,000 points, you get letter grade up. Yeah. So our galaxy, right? It's a disk, as you know. If I use this hand as sort of the representation of a disk, you can imagine that there's spirals. If you kind of look at it, we are kind of here, like halfway out between the center of our galaxy and all the way to the edge of the galaxy. So kind of halfway out. So if we're looking, we can look in the direction of the plane of the galaxy where all the almost all the 100 billion plus stars are in. And then we can see that streak of light, and that's just dense stars. Galileo Galilei was the first person who used a telescope, look up there, and then wrote about the fact that when he looked at the Milky Way, it wasn't just a cloudy looking thing, it was actually lots and lots of little tiny stars, right? So you see a streak going across, and depending on where you're looking in the sky or different times of night or day, or whether you're on the northern hemisphere or southern hemisphere, you can see the shape of this Milky Way. This is basically the disk, the plane. And if you go out at night, you can actually see it when it's really nice and dark. There's a Milky Way, as we see it from the sort of New York City area. It goes from the sort of through the constellation Cygnus the Swan kind of. Anyway, it's really, really pretty, but it's hard to see in the bright lights of the city. But don't worry, someday you'll see it, and it's really cool. This is a longer photograph. It's taken from It's taken from a place called the Cerro Tololo Inter-American Observatory. It is a cool place, by the way. If you ever want to go to see a really neat thing in the southern hemisphere, go to Cerro Tololo. This telescope is huge. Okay, this is a smaller telescope in a dome, but this telescope is actually about 15 feet across, about 35 feet long. So this building is like a 5-story building. It's huge, it's big, beautiful building. Actually, it's much bigger than that. This is the garage door. So if that's 1 floor, 2, 3, 4, 5, yeah, it's really huge. Anyway, the telescope is pointing away. You can see through these window slats over here, out through the main telescope dome slit, and you can see that telescope. You can't see the telescope from here, but it's basically aimed looking this way. Anyway, somebody set up a parking lot camera in this parking lot, which is cool. And you can see, look, these two blobs, they are irregular galaxies. Now think back to early in the semester, we talked about these, right? Henrietta Swan Leavitt. Remember, she was figuring out variable stars to use as standard candles? If you don't remember, go back and review this stuff. This is great stuff, okay? And it's also in the chapters. So if you're going to read about chapter 26, 25, go ahead and read them because there's some really neat stories about them. But Henrietta Swan Leavitt used Cepheid variable stars in this blob, the Small Magellanic Cloud, to sort of help her calibrate the distance scale that helped Edwin Hubble figure out that the universe was expanding, or for that matter, that even the Andromeda Spiral Nebula was actually its own galaxy outside our Milky Way. But this is the Large Magellanic Cloud. That's the Small Magellanic Cloud. There's about 170,000 light years away from us. It is about 220,000 light years away from us, right? And remember that the Andromeda Galaxy is 2 million light years away from us. So these guys are really close compared to Andromeda, but they're smaller too. These guys contain maybe a few 100 million stars at most. So it's a much different scale from our few 100 billion star Milky Way. Okay, so anyway, this is the central part of the Milky Way. So you can just see how much bigger it is compared to these guys. And these individual features, they are very cool. One of these days, if you want, go take a look at them. They're really fun and neat to know. And we'll take a tour of this some other time. It's very cool. All right, moving on. You can see the key point here. Now that you know what the galaxies look like, we want to know how they change, right? Galaxy evolution, I think I've mentioned this before. Galaxy evolution is the research that I do in my life. I study how galaxies change and evolve over time, right, which is really cool. And think about this evolution, right? Evolution in astronomy is basically aging. We talk about how does the universe age over time? How does it change over time, right? This is not the biological concept of evolution by natural selection, which is something that we observe here on Earth and life and things like that, right? DNA-based life primarily. But out in the universe, things change all the time. And those galaxies are like the cells in the human body that tell us, oh, you are an infant, or you are as a system, right? You're a toddler, or oh, you are entering adolescence. Oh, you are in adult times, or that sort of thing, right? So that's the kind of thing that we're doing to use to figure out how galaxies evolve in the same way that cells change or things like that, or that humans change. And so that's what galaxy evolution is to me. And you should read this a little bit. It's sort of a description, right, of how galaxies change over time. And there's more evolution galaxies details about the evolution and distribution. But now, what are different galaxies like? Well, let's take a look. Properties of galaxies. Now, here are the things that I want you to look at, right? This is individual information about galaxies. And so like masses of galaxies. And this table is something that you should kind of get a sense of, right? How many stars they typically have? What is their mixture of stars? What is the amount of interstellar matter that they have that might create new stars, right? And then there's the mass to light ratio. Remember, we're talking about dark matter, cosmological dark matter. Well, how much dark matter is there in these galaxies are compared to the amount of luminous matter? Right? So there's a mass to light ratio also there. And also, if stars are much brighter compared to their mass than, say, the sun is, or dimmer compared to the mass of the sun, that also will give you a sense of how old and how young the stars are and so forth. So mass to light ratio is a cool thing to know. Ooh, beautiful galaxy picture. Love that, M101. Why do they call it the pinwheel? Does it look like one? Yes, it certainly does. So this is really kind of cool. So you can understand how you study galaxy stuff and learn about dark matter and so on. And then we talked about the extragalactic distance scale. Remember this? This is early in the semester. So if you want to get a review of what we talked about, how you find things that are really, really far away, yeah, that's how you do it. And so that's cool stuff to read. And then the expanding universe, this, remember, 26.4 and 26.5. Again, these are review, but if you want to, it's not a lot of text here, but it's a great explanation of that Hubble law, Milton Humason, how they were doing all this great stuff, right? And distances. We did these calculations early on in the semester. So if you want to go and take a look, I encourage you to do so because it's kind of fun, 26.5. But okay, so we got it. We're going to come back here and just reminding you. All right, so galaxies 26.1, 2, and 3 are the key things that we want to talk about as far as galaxies are in this environment. And then here's chapter 27. I just wanted to point to this part to you because it talks about quasars. Yes, it does. We were talking about those QSOs, remember? How quasars are discovered and so on. Okay, so this again, jumping back for now, because you don't want to just stare at a textbook page all day long. What point is that? You got the galaxies, right? I want you to read these. It'll be part of the study guide. Hope you're filling out a study guide already. You're going to be reading and understanding more about these galaxies as far as galaxies exist are concerned. And then the evolution of galaxies, how it changes, how they age, how they grow. And what is the deal with these quasars, right? Remember, we're talking about how black holes exist, and then the black holes grow bigger. And as they consume material, as stuff falls onto them, they get more massive, and thus they're attracting even more material. And under the right circumstances, if they're attracting a lot of material, like let's say they're eating an Earth's worth of material every couple minutes, right? Then they have this massive amount of energy release that's coming off of the material that's coming toward them before they get consumed by the black hole. Remember, we were talking about that in the previous lecture, right? Only a few percent of the material, maybe 10% of the material that fall onto the surface of the black hole actually go into the black hole, causing the black hole to grow larger and more massive. Instead, the materials falling in get so hot, temperatures of millions, maybe even hundreds of millions of degrees. And there's so much energy. Remember, the stuff is flowing like almost the speed of light, right? As they're getting closer and closer in, it just blasts the material outward. Thus, the material that never actually quite reaches the black hole, but all that material comes out in the gravitational engine thing, right? We're talking about tremendous amounts of energy. Even if the nuclear physics, we're talking about that 0.7% of the matter being fused from hydrogen into helium turns into energy. In this case, we're talking like 10 times that amount. Whoa, that's huge, right? Tiny little bits of matter, just as we had said before, just to remind ourselves, right? I took a paper clip. And I said, if I take a paper clip's worth of hydrogen turned into helium, the resulting energy release is equivalent to a tactical nuclear weapon. Imagine getting 10 times that much from the same amount of material. But instead of converting from hydrogen to helium via nuclear fusion, instead, you're just dropping it toward the surface of the black hole. That is a lot of power. And that's how quasars get charged, right? And so eventually you get a black hole. And what it turns out is that black holes turn out, when they become quasars, they tend to be right near the middle of their host galaxies. That's right. Black holes don't just sit in isolation. They're in galaxies too, just like the stars, right? Just like the material that's around that's been swirling in and falling in over all this time. As a result, right, you get a circumstance where the black holes, the biggest one, migrate toward the middle, right? They fall down toward the center of their galaxies, or maybe galaxies gather around them with them at the centers already. It's hard to know which started which way, the chicken or the egg, but either way, the result turns out that you wind up with big, big black holes that are millions or even billions of times the mass of the sun at the centers of galaxies. And when that happens, that's when you get activity. That's when you get quasars forming. Okay, so getting back to that aspect of things, I want to touch back. And once again, section 27.1, talk about quasars. Okay, they all go through redshifts in this textbook now, and that little dot, see, look how it looks just like other stars in this black and white photograph, right? These stars here, they all basically, but this sucker turns out that it's at a redshift, right, of 0.36. So that's huge, 67,000 miles per second. So that's so far away that there is no way that there's actually a single star. And so those kinds of discoveries, right, by people like these two dudes, Alan Sandage and Martin Schmidt, they're laughing and having a good time talking about quasars and so forth. This guy, Martin Schmidt, okay, and this guy is Al Sandage. They're both giants in the field of astronomy and so forth. Martin Schmidt is super cool. And okay, I just have to brag. I'm not even going to humble brag. I'm just going to plain brag. Martin Schmidt, this guy in this textbook, great guy, hilarious, funny, friendly, and super sharp and smart, nice guy, great guy. Martin Schmidt had a graduate student who became a PhD and an astronomer, and that astronomer was my PhD advisor. So I'm the academic grandson to Martin Schmidt. Yay! Of course, I haven't done even like a tiny fraction of the amazing scientific stuff that Martin Schmidt did. So, that's just the way it goes. I don't mind. I have a wonderful, and by the way, my thesis advisor also did great, amazingly great stuff in the field too. So that's wonderful. It's too bad that I haven't done as much as they have. Sorry, guys. but I'm very proud to be the fact that to be their academic grandchild. It's pretty cool stuff. Anyway, I just wanted to put that in there. Sorry, it's just like my personal like pride. I'm really, really proud of that because it's great to have ancestors. Well, they're not dead yet, right? But it's just great to have people who have helped me become where I am today. I really appreciate that, and I couldn't have asked for better role models and better advisors and that sort of thing, better academic forebearers than these folks. Just wanted to throw that in there. Thanks for bearing with me for a minute as I brag about that, because I'm just really proud. Anyway, never minding that. Martin Schmidt, okay, this guy, and Al Sandage, this guy, they worked really hard to figure out what was going on in terms of like what the Hubble constant was and what quasars were. And I explained to you that quasars had supermassive black holes in the middle, but this guy, Martin Schmidt, was one of the first people to figure that out. And even then, it wasn't 100% certain. This is in 1963 when he first started coming up with these ideas and trying to interpret the data that had come in. They couldn't quite figure out what they were. Right? They figured out that these quasars are basically high redshift, distant black holes in distant galaxies. And heck, for that matter, it wasn't even until the Hubble Space Telescope was launched, 30 years ago or thereabouts, that finally people actually figured out that there were black holes in the center. They seemed likely to be black holes, but when I was a student, that wasn't even 100% certain. Now we're pretty darn certain that they are supermassive black holes in the center. But anyway, read this because it's fun, okay? And kind of talking about what quasars look like, and there's your redshift calculations, right? And you're getting more into it and more deeply, which we talk about, right? Quasars obeying the Hubble law. Here's some pictures of quasars and their host galaxies in the taken with the Hubble Space Telescope back in the 1990s. Wow. Notice how all these galaxies, they've got all different kinds. And these galaxies, they have these supermassive quasars in the middle and the size of the energy source. Lots of great stories about that. Here's examples of what happens when a supermassive black hole in the center of a galaxy, a quasar, is bursting out some of your energy. Remember I telling you about the energy, right? The energy is coming out in huge blasts. And if you take a look at this using X-ray telescope, a radio telescope, visible light telescopes, right? Look at that structure and shape. From here to here is like the distance of the diameter of our entire Milky Way galaxy, right? This is huge. So this is blasting stuff really, really far away. So these quasars are basically the brightest examples of galaxies that have active supermassive black holes in the center, right, at their nucleus. So this kind of galaxy is called an active galactic nucleus, or active galactic nuclei, or active galaxies, AGN. So AGN are a kind of thing where you have a supermassive black hole and happens to be getting a lot of energy putting out from it because of all the material that's falling down toward it. And some kinds, the brightest kinds typically are called quasars or quasi-stellar objects, but there are other kinds too. I'm not going to get into them now. I wish we could, but you could have an entire graduate class about AGN, about quasars, lots and lots of cool stuff. But the fact that you know that they exist and they're part of the whole universe is super cool, okay? I want to show you this, by the way, galaxy. Okay, that's the center of a galaxy called M87. All right, and the reason I want to jump to M87 and talk about it some more, we'll come share this screen in just a moment, but I'm going to jump ahead and I will type in M87 black hole, okay? And why? Because this black hole, remember, that picture is taken decades ago, right, with the Hubble Space Telescope. And what happened was astronomers just a year or two ago took a picture of this supermassive black hole. And this time, it did it using a worldwide network of radio telescopes called the Event Horizon Telescope. Here's your thing, right? See that jet that we were talking about earlier over here? It was a picture taken later. And as it turned out, that supermassive black hole, I wish they have it here. There it is. Imagine if you looked all the way down to the center, like the little tiny itty bitty bit. All right, I'll just show you the one picture here again. Imagine if you're looking right at this very, very center here, okay? You are so blinded, right, by all that bright light, right, where that cursor is, you can't see what's in the middle, right? But if there were something that you could get rid of all of that light, just focus in the very center, like have baffles or something, and really look at the very, 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 very center, and don't get blinded by all this extra stuff, right? Try and look at, so imagine looking, if there were like a little tiny dot, like a black dot in the middle of this bright searchlight, you're like, I can't see the dot. But if you somehow focus all the way into the very, 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 very center, right? Really, really in the center, what would you see? And that's what these folks with the Event Horizon Telescope people did. They looked right down the center. Oh my gosh, look at that, right? This is what they saw using these radio telescopes that were calibrated with super, super sensitive characteristics. Wow. The professors, the colleagues who did this, Katie Bowmans at Caltech, she was one of the people. She did that while she was at Harvard as a postdoctoral scientist. There are a bunch of others at Harvard, at MIT, and all over the world, really, that were doing all this stuff in South America, in Asia, in other parts of America, Canada, Europe. I mean, thousands of people collaborated to make this happen. It was really amazing. So this is looking right in the center. All right. So this black blotch here is about the size of our solar system. All right. Maybe a little bit bigger. But inside that blotch, behind that blotch, at about the size of the cursor that you see right there, in other words, about 1/3 the diameter of that black blotch, is a black hole, a supermassive black hole that's billions of times more massive than our sun, our entire solar system, right? So in the size of our solar system, but billions of times more massive, the supermassive black hole. And the light that's shining, right, is being distorted like crazy around this black hole because of that gravitational influence. It's literally warping space and time around it and creating these weird shapes and so forth. So our eyes can't see that because it's the wrong kind of light. But just imagine being able to understand and see, oh man, look at all this great stuff, right? This is where it is in the sky. That's like patches of information. And if you want, go to this, right? And you can see the zoom in over time, right? When they were looking and trying to find all different things. So at some point you can look at all of this because it's fun, and use the Wikipedia page, all right, which is totally fine. So I'm going to go back to the Wikipedia page. Oops, just there it was. And so take a look at this. I want you to read through this just for fun. There's some technical jargon in here, but there's the really good core stuff about a supermassive black hole, which we have now taken a picture of. There's actually a photograph. I mean, black hole you can't see because the light's going in there, right? And it's got this little round blob of blackness all around it, but the black hole's there, and everything around the outside is glowing, and it looks weird. It is awesome. All right, that's supermassive black hole activity. Yes, quasar type stuff. It is awesome, people. It is great. I love this stuff. Okay, anyway, let us not get overly excited. Now let's get excited. It's great, man. Black holes, they do not suck. They are awesome. Yes, they are. And these supermassive ones are pretty awesome too. Pretty much every single galaxy that has any reasonable size, like the Milky Way or above, right? Every one of these galaxies has a supermassive black hole in the center. Our Milky Way is no exception. We have a black hole that weighs about 3 million times our sun. Okay, so it's not that huge, actually. Yeah, if you actually measure its size or so, it's maybe a few times larger than the sun, but it has 3 million times the mass, and it's sitting in the middle of our own Milky Way galaxy, not billions of solar masses like this M87 black hole, but it's still millions. And so we have one too. Yes, and there's a lot of them all over the place. So knowing how black holes work inside galaxies is a really, really important part of galaxy evolution. Right? Galaxies, when they collide, they have black holes in the center. Those black holes have to collide, and they wind up sending out these amazing things called gravitational waves. So much good stuff. So much good stuff. Oh, if we had another whole semester, I couldn't finish telling you all the cool stuff that there is. But we are running, to the point where we're reaching a nice conclusion to our class. Oh man, can't believe we only have a few lectures left in the semester. Oh, there's so much cool stuff to talk about. Anyway, let me get back to that. Last little bit, I want to talk about supermassive black holes and quasars and galaxy evolution for this lecture, and then we'll move on to the next lecture, okay? And I hope you're still doing your study guides, right? Okay, all right. jumping back to the black holes and the quasars in astronomy in the textbook, right? That's section 27.1 and then 27.2, right? Supermassive black holes, what they really are. And the fact, that the people who wrote this textbook, Andy Fracknoy, David Morrison, and Sidney Wolf, great folks, actually. They are talking about the history of finding what black holes are based on all of those decades that they were involved in the discovery of these cool things. And like understanding, are they black holes or not? Oh, there's the picture of M87, right? The black holes, that little fuzzy version. The more sharp version came out in 2021 because they refined additional data and got additional cool information about it. So notice like all of these galaxies, right? Here's another galaxy. This is a disk around the black hole. This is not the same kind of disk we saw, right, in M87. Notice it's an elliptical galaxy, kind of just like M87 is. This is a disk of gas that's swirling around the outside, the bright part in the middle. If you imagine zooming into that really, really bright dot that the cursor is pointing at, and then using that Event Horizon Telescope, seeing what's going on, that's what you see up here. So this blotch here is actually buried in that dot way down in there. So imagine the telescope technology that's producing this stuff. And then the energy production, as I was telling you earlier, right? You can produce more energy in 1 second for most quasars that you can wind up producing on the Earth via the sun. Why not? Let me rephrase. It produces more energy in 1 second, these quasars do, thanks to things like the falling. This is the description of like the heat that you can generate when you're falling in through a dense material, like the accretion material, the thing that's falling in the black hole. You can generate more energy in 1 second with all that than the sun can produce by nuclear fusion in 1,000,000 years. That is pretty amazing. So here's all this cool stuff that I encourage you to read. Here's a description of those jets, right? Oh, here's a great example of those jets. Remember that disk that we were showing earlier? Yeah, so this is a radio telescope image again. And notice that in this case, these jets out this way, right? Each one of these is as long as the Milky Way is crossed. So these are big, beautiful, powerful jets. And they zoom all the way in the middle and you see this. And if you zoomed all the way in there, if it were possible, then you would see that Event Horizon Telescope picture of something like the M87 disk. So you see how these, now this is really interesting, right? This is, I would recommend you read this for entertainment, describe sort of what people thought about, how people thought about astronomy, right? If those of you who are interested in history of science and how people went forward and learned about what objects were. Remember when Edwin Hubble was trying to figure out the distance objects, and there was debates about the history of the universe, whether it's young, whether it's old, whether it's expanding, whether it's not, whether galaxies even, right? Remember the great astronomer Harlow Shapley and the great astronomer Hubert Curtis. Harlow Shapley didn't think that the data showed that the universe was expanding for a long time. Right, it took a long time. So that's an interesting paragraph or a discussion. Martin Schmidt talks a little bit about, what does it mean to be like thinking about astronomical or even other kinds of scientific questions there on the border of what we know and what we don't know, right? Great questions. Anyway, how do we wrap up this lecture? Think about galaxies and the black holes inside them, right? And how they're doing their thing. Our galaxy at some point forms in all of that maelstrom, right? So now it is time to tell you when our Milky Way galaxy forms. The first galaxies form around redshift 7. Okay, then there's redshift 6. Then there's redshift 5. Then there's redshift 4. When do you think the Milky Way galaxy forms? Redshift 3? Turns out that the Milky Way galaxy forms around redshift 2. Right, that's 10 billion years ago. It's about 4 billion years after the Big Bang. And I'm going to write this in scientific notation. About 4 billion years after the Big Bang, at redshift 2 is when the Milky Way forms. Most galaxies form around that time in the universe, as far as we can tell. The Milky Way galaxy forms around the same time as a peak of galaxy formation. All right, I guess I should be careful. It's not necessarily that more than 50% of galaxies formed at around redshift 2. But galaxies form all the time, right? They form over a long period of time, over billions of years since redshift 7. But it turns out that right around redshift 2, that is about 10 billion years ago, maybe 3 to 4 billion years after the Big Bang, that is when more galaxies are forming around that time in the history of the universe, right, than any other period of time that we know of in our research and study. There you go. You want to know when our galaxy formed? We're talking about the timeline of the universe. We're talking about redshift of gazillions up here, right? Down, 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 down. And a few seconds nucleosynthesis, then a few 100,000 years before we get the cosmic background radiation, right? Redshift of 1,000, and then redshift of 20, that's when the first stars form. Redshift of 10, reionization. Redshift 7, the first galaxy. Redshift 2. It takes 4 billion years to get to us where the Milky Way galaxy forms. Pretty cool, right? So our entire history of our galaxy being in this one huge universe really gets its start. We are well formed. We're basically bits and pieces. Remember, thanks to the hierarchical structure formation, like bits and pieces of the Milky Way have been assembling over long periods of time. But by redshift 2, it's pretty clear that that's when our galaxy really exists as a galaxy. So, cool piece of the timeline of the universe put back into place yet again. And in the next lecture, we got one more step, right? We got the galaxy now. We got a whole bunch of stars. What's the deal with those stars? We have some sense of galaxy evolution. Now it's time to understand stellar evolution. That's the next lecture. It's awesome stuff. Thank you so much for your time. Remember, fill out your study guides, right? If you have any questions, ask me, ask your recitation instructor, ask your lab instructor. We got great stuff to talk about. Thank you so much for your time. Go back and read all this stuff. Remember, I'll try to use the study guide to guide you in that respect, but really, really appreciate and enjoy this stuff because this is the universe turning into stuff we recognize today, the stuff all around us, right? Talking abstractly about the whole cosmos for a long, long time. And now these are the things that we see in the night sky. That's where they're coming from. And that's where we're going next. Thank you so much for your time. We will talk again in the next lecture, okay? See ya.